Thanks very much for your time, IEEE colleagues. This is Mike Anthony, and thanks for calling into our teleconference. We have the pleasure and the privilege of having some expertise and time from Michigan State University to discuss, to add to our catalog of campus power system overviews. As you recall, last year we did Michigan Tech, University of California, Berkeley. We also did Lawrence Livermore Labs, and we also did MIT. My hope is here early this year we'll do the University of Michigan and Harvard. So I guess what I'll do is just get started with introductions, and far in the other time zone is Lauren Clark at the University of Alberta. Lauren, you want to introduce yourself and say a little bit about what you do there?
So as you said, I'm Lauren Clark. I'm the electrical engineer with electrical utilities for the University of Alberta up in Edmonton, Alberta, Canada. I've been here for 11 years, and I do project management and design and whatever else they tell me to do that day.
That's what you always say, Lauren. Let's see. Go ahead, Ken Beach.
Yeah, Ken Beach, electrical engineer here at Michigan State University, working in the infrastructure planning and facilities group. Been with the university for a couple years now, and basically have responsibilities for campus distribution outside of the TB Simon power plant.
And let's see, we have Kane Howard. Go ahead, Kane.
Yeah, I'm Kane Howard. I've been with Michigan State about 10 years now, and I do mainly electrical, project engineering, lighting, and I work for infrastructure planning and facilities.
Thanks, Kane. And Bob, can you hear me? I don't see you on the call, but I know you're in the room. Go ahead, Bob.
Yeah, hi, this is Bob Ellerhorst. I'm the director of utilities here at MSU. Civil engineer, 40 years in November now, 40 years. So, and I hope I'm going to spend a little bit of my time just trying to give you some of the history that I'm aware of as far as my part of this presentation.
Well, I like that, Bob. History that I'm aware of. Hey,
the history that I'm aware of.
I always like to remind people that I took my graduate power system courses at Michigan State University in the 80s, and I would stop by Bob's office up at the Simon Powerhouse from time to time to say hello. So I guess he, like me, knows where all the bodies are buried, and that's why they keep them around. So probably among other reasons. So I guess what I'll do is I'm going to turn the airplane over to Michigan State, our colleagues at Michigan State. I guess we're looking at Ken Beach's screen, and it's your airplane, Ken. Go ahead.
Okay, first I'll end Rick Johnson's with us also. Go ahead, Rick.
Rick Johnson, electrical engineer and controls engineer here at the power plant, responsible for all the electrical systems and control systems in the plant, also campus utility metering in all the buildings. Been here about 25 years.
All right, so with that said, I'm gonna go to the next slide, and Bob, the historian, is going to lead us off.
Well, again, how we got here, being a land grant institution, we're similar to a lot of the other Big Ten schools that, in the 1850s, we were landing in our communities before there was utility infrastructures. And so, a pretty common story in the Big Ten, I think, is that we all, started on this journey of trying to provide campus utilities as part of our facilities responsibility for our institutions. I think similar, a lot of us went to central plants. We went to Central Plant in the 1890 and did some electrical generation for street lighting right around the turn of the century. But we kind of, as we were a small university and not really growing large until after World War II. So the significant change for us came, and we were fortunate in that we're not a landlocked utility infrastructure where a lot lot of our other sister institutions, quickly got captive to property. So we were, we actually, if you can back up kind of the slide, on this particular slide are two of the, you can see on the left of the slide our current location that was constructed in 1965. On the right of the slide is a property that was built in 1948, and its predecessor was built at the turn of the century. So we are actually fortunate enough to be able to relocate our utility infrastructure, our generation, twice from the original. And then what became significant in 1958 for us was when we put our first CHP unit. It was a 3 megawatt GE unit that we put in. We were already at that time committed to a 4160 distribution, and I don't really know when that voltage got started on campus, when we started a 4160 distribution. Rick, I don't know if you've ever heard that one. But we continued the 4160 distribution on campus until this plant was constructed in 1965. And that, so I would say, we're supporting 20 million plus square feet from this facility. And in 1965, that number was probably 10 million square feet. And so we got about 10 million square feet that was constructed at 4160. And then since then, our campus distribution has been built on the 13.8, and Rick and Ken will talk to you about that afterwards. But then when we built this plant in 65, we made the real significant decision to put in cogeneration. And again, the plant was balanced between, we were, 1965, we were really not we just becoming a heavy research campus. And so our buildings were really balanced between our requirements for steam and electricity. And it really wasn't until that we got into the late 70s and the early 80s, just like everybody else, that our electrical demand started taking off on us. So, so Ken's got up some data related to the plant that we've got now, which is really geared towards being providing a lot of condensed power for campus, providing a co-generated power, and we can do that through extraction turbines, and so we got one back pressure machine, and we've got four controlled extraction condensing turbines, and then we got a combustion turbine that we added in 2006 for black start. So that got us to the point that I'm talking about up to about 206, and then I'll let the other folks talk about where we are now and how the system operates. But we got to about 206, and we believe that our costs to provide power, even though we were providing perhaps 40% of our electricity in today's model using our condensing functions on our turbines, we believe that we've been highly competitive, price-wise on our power production. And that's really the challenge for us going in the future is really what are we going to do with that power that we're currently using those condensing turbines for? How are we going to make it in the future? So that's probably the next generation for our power plant, the question that needs to be answered. So I know that's again, snapshot in history. The slides here have some facts and figures. We're nameplate 100 megawatt plant. We're a peak electric demand 67 megawatts. This Christmas break, kids just returned Monday, of this week, Christmas break, we were sending the campus about, Rick, I think we were sending 380,000 pounds per hour to heat the buildings with nobody here. Electric demands were just under 40 megawatts with nobody here. So basically, you know, we got this campus that we're in winter break that's chewing up 40 megawatts and 400,000 pounds of thermal requirements, and campus is closed. So anyway, that's what I hope to share, for at least to start the conversation.
Rick, anything?
Any thoughts on that?
Mike, any questions at this point on the plant?
Yeah, I'm sorry, I had myself muted. So what is your cooling mix? Electric, steam, electric or steam? Are you able to use some of the steam for cooling?
Yeah, the historic demand for us for cooling in the summer, you know, is help me out, Rick. I would say that if it's 90 degrees outside, campus population is here. We've got a campus load that might have been 500,000, just short of 500,000 to support absorption cooling on campus.
Yeah, that's about right.
Is that about right?
I think so.
And that creates one of the challenges going forward, you know, commensurate to what Bob was referring to, is that going forward, cooling will be electric chiller versus steam absorber due to efficiencies. And quite frankly, we have quite a few steam absorbers that are at end of useful life in the near term. And so a campus master cooling plan has been developed that calls for about 20 megawatts worth of electric-driven chiller cooling over the next 20 years. And we have a campus infrastructure from a duct bank perspective and distribution perspective that's predicated off of the steam absorption approach. And so we have you know, potential challenges coming up in the next 10 to 20 years.
Yeah, this last week the plant was cruising at about a 67% efficiency. You know, we're making money, good time of year, you know, sending out steam and low electric demands. We're probably trying to make 40% efficiency in the summertime with the historic practices of, you know, using where we've got 60 megawatts and we're making 30 megawatts with our send out to campus. And the rest of it though, we could make condensed power cheaper than buying it on the grid. Our interconnection with the grid has only been 21 megawatts and it was on distribution tariff rates. So until just recently, we haven't had transmission service. So the game's changing for a little bit. And again, I don't want to jump ahead. I'll let the other two talk about where we are now with that.
This is Bob, Mike again. Are you condensing anything? Do you have dump condensers?
You call them dump condensers.
Well, this is, we simulate a load, like University of Michigan, we have a 6, I'm not sure, they may have increased it to 10 megawatts, but when we don't have the steam load, we have the electric load, it helps balance it out. It gives you a little bit of a margin. It's a wasteful, admittedly it's wasteful in terms of BTUs, but it's more economical. You guys know that trade-off with the cogen plant. I was just curious to know if you have a way to simulate load with a condenser.
If you're talking about a configuration like a normal electric generation plant that is wasting heat to a cooling tower, for a normal utility cycle that's running at 35%, yes, we have that capability. We have cooling towers that we can waste off, and so that portion of our generation, we're only at a 35% efficiency on that piece. So
yeah, it'd be nice if the plant campus planners could, if you're operating your plant, you've got a lot of. Is it ever possible to change the utilization during the break? Your break is what, 3-4 weeks? Or the better part of 3-4 weeks, isn't it?
Yeah, 3 weeks this year.
Yeah. Okay, that's all. Thanks.
So on the screen now is this is Rick, our plant electrical one-line diagram. It's probably a little bit hard to make out all that, but you can see our 6 generating units. We have 6 distribution buses to campus at 13.8 kV, generating at 13.8 kV, obviously. So each generator has a distribution bus associated with it. Each pair of generators, 1, 2, 3, 4, and 5, 6, have generator bus ties between them that are normally run open. Each distribution bus, we've got 6, so 3 pairs are connected to 2 different transfer buses, transfer bus 135 and 246, and those in turn are connected together at an interconnection bus to tie everything together. So we've got a lot of flexibility. So there's basically 2 connections to each distribution bus. We can have generators off and close a generator tie bus and backfeed wherever we want to. So a lot of flexibility in this setup. It's easily expandable. We've got a lot of reactors, a reactor on each between each generator bus and distribution bus. We've got reactors on our transfer buses before the interconnection with our utility tie. Like Bob mentioned, we up until October of this year, we were on a 46 kV to 13.8, 25 megawatt basically substation, 2 transformers in parallel. We've ran that way since the plant was built. We added the second one in like 1989 or something, but so we finally, with the FRIB, you're familiar with the FRIB project, quite a large electric load coming on campus with not much steam demand, no steam demand really. So the university decided to purchase that power for the FRIB. So we built the new substation. Consumers Energy built the new substation for us, still partially under construction. It shows a picture of it here. We've got one, the substation's in the same footprint as the original one, so they built the bank on the left first, and we switched over to the new sub, and then they tore out the old substation that was on the right, and now they're in the process of building the second bank there. There's room in the middle, and all the foundations are going to be in place for a third bank in the future. So that ties in. We added a switch house out there, the little building. It's got a switchgear line up in there with distribution breakers. We're running a little bit short on distribution in the plant, the distribution breaker space, so we added breakers in the switch house that we can feed. There's 4 circuits that are dedicated for the FRIB. We could bring in solar or whatever we want into these breakers here, or feed other distribution as we see fit. So that's basically the plant.
All right, next we'll talk a little bit about the campus power distribution. We've got we distribute from the plant off of the buses in circuit pairs, 13.8 kV. There's 11 circuit pairs, plus there's a lone circuit, which is circuit 60. That circuit is considered the priority circuit on campus that currently powers the administration building, the computer center, the communication arts building, the Department of Public Safety, and a reservoir, and that's our #1 circuit. All buildings on campus are served by 2 circuits throughout. So when we distribute in the circuit pair, each building is set preferred to a particular circuit, and the complement circuit then stands ready in the event that there's an outage. And all buildings, as you can see on the screen, are configured primary selective, secondary selective. Distribution throughout campus, I have a one line coming up here in a second. that just a generalized one line demonstrates that the campus power distribution is radial in nature, and then all power distribution on main campus is run underground, and we've got over 15 miles of duct bank installed and more going in as I speak. We're fortunate. We have a full complement of electricians, both medium voltage and then what I'll call lower voltage, or the 600 volt class. But we now have 9 full-time medium voltage electricians. And campus is a busy place these days, a lot of work going on, and we self-perform all medium voltage work on campus. So, as I said, we've got a lot transpiring as I speak. Primarily, our campus feeders are comprised of triplex, 3-conductor 500, KC mill copper, EPR, and there's the occasional run that's in 2-watt or 350s. Unlike some of the other presentations in the past, we have very, very few faults here on campus. Talking with director of our field installation crews, can't remember a time that we've had a bolted fault or a phase-to-phase fault, with the exception of a squirrel that got into a cabinet. Aside of that, the occasional failed splice, we'll get a single line to ground a fault, and on average between 1,000 and 1,200 amps, I think, Rick, is the last 2 or 3 that we measured were plus or minus. Buildings in general, there's 59 buildings that have emergency generators. As it relates to optional standby power, each department on campus is responsible for procurement and maintenance of their own generators. That would be in the research facilities, the medical facilities, and that would house specimens, samples, medications, what have you. And then here's the generalized one line of the campus. The blue squiggly is actually the Red Cedar River that separates North Campus and South Campus, North Campus being the original. And then the T.B. Simon power plant's demonstrated at the bottom of the one line. What is in blue is the interconnect to Consumers Energy. And as you can see, we basically run in circuit pairs. And it'll alternate. Most of them are, circuits from bus 1 and bus 3 will run together. Buses 2 and 4 will run together. We've got a couple situations where circuits 13 and 53 are our newest circuit pair. They were installed here over the last 6 months up at the corner of Kalamazoo and Harrison on the west side of campus. We have a new 11-building student housing complex that's being built, and that new circuit pair was installed to support that, as well as we just recently converted the Kellogg Hotel and Conference Center and the Brody housing development from circuits 1636, and we converted them to 13 and 53 to balance some loads out. So we're planning now, we're building a new 10-megawatt data center that's 10-megawatt compute. Speculate that that'll be a 14-megawatt load. We've got a new circuit pair that's under development for that. And then we have another new circuit pair, 69 and 49, that we're going to run to East Campus to support some growth in that neighborhood in the southeast corner of campus. Got another, hang on for the slide. Now this graphic shows you basically campus, and the color coding is circuit pairs, and that's the basic distribution. This map is the configuration just prior to Christmas. In the upper left-hand corner is the Brody Complex and the Kellogg Hotel, and they are now converted to, I guess, the color brown. That would match then the housing complex I spoke of to the south of that. So this map does, in the upper right-hand corner, you can see the circuit pair configurations, how they run in tandem throughout the campus. And then we alternate the buildings, which is preferred to a particular circuit. And then through balanced loading, we may swap a building on a particular circuit. The typical building service equipment, as noted, we serve each building at the 13.8 kV. S&C's System 2, the old System 2 gear, now they call it their custom gear with micro AT throw-over control, serves each building. And then we've got double-ended subs in most of the buildings. And so what you see in the lower right corner is a building that would have, that particular one has two single-ended subs. That's the vault outside of the IM Circle Sports complex. And that each one of those switches on the right serves, one serves a 480 sub, the other one serves a 208. The picture in the upper left, that serves a building that's got a separate 480 volt double-ended sub and a separate 208 double-ended sub. And then here's a picture. The upper left is the newest building on campus, which is the bioengineering research building. That's the 480 volt substation. And then on the lower right is the 208 sub for the IM Circle complex. And so that kind of gives you a sense of how we distribute and how we're configured in each of the buildings. The priority buildings, as noted, have separate 480 and 208 subs, and they're double-ended for the secondary selective. So any questions at this point?
Mike Anthony here. Do you have it seems to me that your preferred way of feeding a building is at medium voltage with a substation, a dry type substation somewhere in the building. Is there a load criteria? And here's what I'm getting at. Very often in campus environments, you may find lower power densities. You may find an entirely new building may only have a computed load of 338 kilowatts. And that can easily be fed at 480 volts, say at less than 1,000 feet. And I'm curious to know if you have a practice out there of extending 480 volt feeders to feed moderate to small size load centers or buildings.
We have a few the smaller buildings where we've sub-fed a building from an adjacent building where the load is that small, Mike. All of the subs have liquid transformers, no dry type transformers on the utility subs in the buildings. And then, obviously we try not to load the buildings, each transformer to 50%. There's one building in particular I can think of, the HANA administration building, the 480 sub. We're a little heavy on the one end and at 50% on the other end. So, that's one of the few that once we get the new data center built, the compute load will move out of that building, and the cooling load will come off, that data cooling load will come off of that sub, and so we'll be below 50%. As it relates to the dual circuit feed throughout campus, the circuit pairs, a good case in point, we try not to load those 500s higher than 350 amps. That's taking in the derating factors for the duct bank installations. In 2015, September 2015, we lost a splice outside of the life science building that affected circuits 25 and 45. 45 went down due to the splice. All the buildings that were preferred on 45 automatically switched to 25, and we were pulling 338 amps with load on that remaining circuit. And yet that particular day, the regional chilled water plant was only running at 1.1 megawatt, and it's been known to crest 2 megawatts. So, we keep a watchful eye. We try not to load our cables over 50% so that we have these contingency planning factors in place. And, I got to give all the credit to Van Frazee who established this, and it's rock solid, and it's going to provide service to the campus for quite a long time to come.
So your cables are 500 throughout the entire length? It's primary. I think you're describing a primary selective, main time main primary selective system. Are your cables the same length, size throughout?
Yeah, for the most part. There are some offshoots that, as I noted earlier, there's some offshoots that are 350s, and then the occasional where we jump over and feed a single building. We've got a couple of locations where we've got 2 lots, but we've standardized on a cable, and we have a custom spec cable, so to speak, an MSU standard cable through Keyrite, and it's served us very well.
Mm-hmm. So this will be my last question before I ask Lauren. Lauren might want to pipe in. So I notice here that you have liquid filled transformers, which I think that offers you some benefits in terms of size. Am I mistaken? You're likely to see a liquid filled transformer smaller than a dry type of equivalent KVA.
Right. Yeah, we've seen a lot of benefit from that.
And so your trade-off, though, you have a maintenance, a different kind of a maintenance issue, and because I'm so familiar with dry type, and we have them at our hospital, liquid-filled. What kind of air handling equipment, auxiliary, when you need to move air out of them, is your liquid-filled transformers? Are they less of a problem than, say, a dry type would be?
Yeah, we've got, for the most part, with this approach, there are, dedicated vaults for each of these installations and dedicated air handling system, whether it's exhaust and supply, for each of the spaces. So obviously one of the maintenance challenges is going through and changing filters and things of that nature on the air equipment, but a fairly robust design, from the air side all the way through the power distribution side.
Mm-hmm. Okay. Lauren, do you have any questions?
Yeah, I got a few. Could you go back a couple slides to your area signal line? I'm just trying to understand a little bit more about the topology, that one. So you said you have 6 buses for 6 generators, and they're connected together with ties, and you have circuit pairs. So I'm assuming that basically your circuit pairs are feed-throughs from, say, bus 1 to bus 4 with some kind of an opening somewhere in that circuit between bus 1 and 4, as an example. Would that be correct?
Well, when we talk about the circuit pairs, I'll use bus 1 and 3 and bus 3 as an example. We have a breaker, and they typically, most recently I'll use circuits 10 and 30 as an example. So circuits 10 and 30 feed the new engineering chiller, right? And so we got a breaker for, on bus 1 for circuit 10, and the same thing, a breaker for circuit 30, and those feed out. And then the tie that you're referring to happens in that 15 kV gear lineup inside the building. And then let me go. So here on this slide, we'll take that lower right-hand photograph. So the 2 switches on the left are the incoming switches, and one is normally open and the other one is normally closed. Now we put an orange dot in the window of the circuit that building is preferred to. And then the nice thing about the S&C equipment, it's the only manufacturer we can close couple tie, cross, closed switches, and without any issues. So just like over the holiday break, we did a lot of converting of circuits, as I mentioned, the Kellogg Hotel, the Brody Complex. Simultaneously, Rick had breaker maintenance to do on bus 2 back at the plant. So we needed to clear bus 2, and this gear lineup, this gear arrangement allows our guys to go out to the field and close transition transfer between the two without the building seeing an outage, taking an outage. We can go from the preferred circuit to the complement without any interferences, without dropping the load. And then, it takes some time to do that. I think for Rick's case, it took the better part of the day for 6 guys to go out and clear, 14, 16 buildings that are on that circuit pair.
Are they electrically operated or locally operated?
Yes. Well, they're not remotely operated, but they're electrically operated and manually operated.
So electrically operated locally.
Yeah, versus via the micro AT control that's in the gear. That's the I guess the product name for S&C's product.
Directly upstream of this gear that we're looking at, so do those 2 incomers ultimately start from the generator buses that we thought, the 6 generator buses, or 2 of those 6 generator buses?
The next overcurrent protection device north of those 2 switches on the left end are in fact the distribution breakers on the plant buses in the plant.
Is there some switches between, or not, like non-protected?
No switches in between. We do have a couple of we have a couple of locations where I'll use the example circuits 25 and 45. We splice off of those main trunks, and where we've got to feed 2 or 3 buildings in the south middle part of campus near the recycling center, we've got a PMH switch, pad mount switch with 2 output bays that that is far and few in between, but we have a couple configurations like that. But typically, such as these are, what I'll call our priority buildings, definitely no.
What type of liquids inside of the transformers, out of curiosity? Is it typical mineral oil, or is it something else?
Well, going back to the day, yes, the mineral oil. Today it's FR3, it's biotemp, it's all the vegetable oil, the less flammable, environmentally friendly fluids. We do have we do have our fair share of transformers that we need to replace the oil in. There's 65 of them. 65 of several hundred. But
did the campus start islanded from the utility? I'm still a little surprised that the utility component or connection is only a fraction of what you are using on site. That's unique.
Yeah, this is Bob, and your answer is yes. We built, I believe when the plant got built in 65, we put in 25 megawatts of generation in 65, and we put 11 megawatt interconnection on the distribution for standby service. So, and it's always been a standby service connection with the local utility. And just Michigan is not a deregulated state, and it didn't come without a battle in the 1965 the approval process with the state to allow us to put in this islanding capability for us in 1965. It was quite the interesting battle, I'm understood. But here we are, and we're good friends with the local utility now.
Regarding the utility interconnect with this new sub and a 100 megawatt interconnect, capable interconnect, The facility for rare isotope beams, the FRIB, I think that load, if I remember correctly, is projected to be 18 to 20 megawatts, somewhere in there. And it was discerned early on that they weren't going to power that from the TV Simon power plant, and because it's a Department of Energy project, that they were going to purchase electricity from Consumers Energy. So via that switch house that you saw, the FRIB facility has got output breakers there that feed directly to the FRIB with multi-sets of 750 kc mil conductors. And then we've got the cross interconnect to the Simon plant that will support us if we need it. I guess one of the other things we talk about, I was going to put a slide in here about future, the near-term future. We've got a lot going on in that we're building a new data center, right? A 10 megawatt data load, thought to be about a 14 megawatt total load. That student housing complex is going to be a 3 to 4 megawatt load. The regional chilled water plant is going to have some work done. We're going to grow there. We've got a new interdisciplinary science building in the works. That could be as high as 2 megawatts. I'm anticipating probably 1,200 kW. Let's see. And then we got some customers down on the east end. We got to add another meg plus capability down there. And then we've got, on the renewable energy side now, on the generation side, we just signed a PPA agreement to receive 10 megawatts of solar power. And what that is going to be comprised of is 5 of our parking lots. We're going to put up parking canopies, and the solar panels will serve as the canopies. And then we will receive power from each of those 5 parking lots, bring it back to some gear that we're getting ready to purchase, and input that into the switch house. And that's first step in the President's plan for sustainable and renewable energy migration here on campus.
Any other distributed generation besides the solar you just mentioned?
We've got this is Bob again. We've got a self-service through a digester operation that that's in consumers distribution territory. So it's our generation, and then we've got a self-service agreement. And again, this is all on our contiguous property, but in their distribution service, which is not that in April of 16. Done it through our air permitting process. So we are only single fuel permitted now.
We were coal, biomass, and gas up to that point.
Yeah.
And burnt our last bucket of coal, so to speak. And
yeah, the fuel of choice for based on economics. Way back when, Mike, your team in Ann Arbor was we were paying $2 a million BTU for fuel, and you guys were paying $5 and $6 for natural gas.
Yep.
And we had quite an advantage on you with our coal prices for a long time. So, but now we're both sharing whatever the market is on gas. We're both sharing those good or bad prices.
So, are you on a periodic renewal for both of your utility services, gas and electricity? Every 3 years, every 5 years, every year?
I don't know what you mean by periodic renewal. You got a franchise. We got a franchise situation here with Consumers Energy, and so now the gas supply. We got multiple gas suppliers. We don't have our LDC is still our local utility for delivery of gas, but we've got multiple natural gas suppliers. We got fuel agreements with about seven gas suppliers, and so any particular month, 2 or 3 of them are giving us fuel.
No, I meant you do have you're contracted some standby service with Consumers Power, or who are they? CMS now? I'm not sure what the name jumps around. I think of them as Consumers Power. Maybe there's a different name, but you are negotiating.
Yeah, the parent corporation is CMS Energy. Consumers Power is our local distribution company that we deal with. So they're a subsidiary of CMS Energy.
Just so I'm clear, with the new substation, it's 100 megawatt capable. So basically, you have full utility backup for the campus system now, or is it still stuck at the 21-ish mark?
No, it will be. It's 50 megawatts. It's half installed. It went from 21 megawatts to it will be 100 megawatts in March. We don't intend. So now we have 100% backup on electrical demands for campus. Don't intend to buy that. It's way too expensive. But if the solution, we were chasing the question of how to supply a 20 megawatt load for FRUB, and we looked at building this transmission service to the grid, or install equivalent necessary capacity for self-generation. And we got a $24 million project as opposed to what was estimated at a $60 million project. So we went with the 24 million, which really, we really gave us we've got a great bootstrap now for the university, but it does allow us, if prices in the electric market become favorable, we can buy. We already are buying off-peak. So we're taking advantage of dropping our load at night to drop that condensing power, that dump power, Mike. We're turning it down at night. We're ramping the plant down every night to buy off-peak. And then we get back off of it by 11 o'clock in the morning on those on-peak rates, because our self-generation rates beat the on-peak demand costs.
A notable thing to just bring up, that 138 kV that comes into the new 100 megawatt substation, Consumers Energy pulled that off the ITC transmission network and ran it 3 miles underground.
Yeah.
2 circuits, so that the plant or the substation is fed via 2 circuits from the distribution corridor, all underground.
That was our requirement. Of the 24 million, that was probably, that might have been an $8 million adder, because we demanded it be underground.
Did they use aluminum, or they own that wire, right?
Yeah, they used aluminum on that, Mike.
Yeah. Okay.
And yes, they own it.
Yeah. Okay.
They own it.
Yeah, almost all utility, even Detroit Edison will tell you, most of their underground is all aluminum. Well, it's actually all overhead as well. I getting back to an earlier question I had about your feeders and the sizes of your feeders, and I know how systems evolve over time. What is your longest feeder? And I'll mention this in the context of what we had to do when we were running power from our central heating plant back in the early 60s to the athletic campus. We were starting at, we started, I believe, at 350 or 500 and then to 350, and then we would step down successively so that by the time you got down to the very end, Chrysler Arena, the better part of 2 miles, I believe I measured it at 1.7 miles in its normal configuration, we had considerably smaller feeders. So I guess that raises a question: what is the longest length of any of your legs of your primary selective system?
It's, we're out there a couple miles, Mike, and given the radial nature of the distribution system, there's a lot of green space at the end of a lot of these circuits, aka real estate to grow on in quite a few corners of campus. So it really isn't advantageous to get smaller the farther out you go when you know that you have the potential to add load out at the ends of those feeders. We're somewhat capped now at the north end of campus. The last of the 4160 distribution came out in 2015, and we got the remainder of the buildings converted to the 13.8. I'll see if I can, north of the river, there is an old underground, all right, on this map. Up in the green area, you see the two buildings on North Campus, the two yellow buildings north of the river. Just north of those is an underground distribution vault, very large. It had two 10 MVA buses up there with transformers. That underground vault is still there.
That's the foundation for the original plant.
Yeah.
The 1890 plant, that's the remaining foundation.
So we closed out the 4160 era, and we've since removed the distribution gear and the transformers. We're gonna put a fresh coat of paint on it, seal it, and I fundamentally have some plans for it. So 4160 is gone. The north part of campus, that purple belt, North Campus was that was the last of the 4160 up there in what I'd call the northeast, near that apex in Grand River. That's the road up there, Grand River Avenue.
On this map where Ken just talked about, so he told you where that substation was that fed the campus, that was north of the river, and then the second plant was, if you can, that kind of I guess that's a blue. If you can make out the large blue piece, that's our stadium, and just to the lower right off that stadium is the location of the plant that was built in 1948, and it's got shut down in 1975. And then we moved to the location that's on the southern edge of this map, our yellow plant that started in 1965.
Hear me, there was a technical problem with Citrix. I'm going to reconnect with Ken again, and Ken, you'll have to reaccept it. From time to time, Citrix does drop, and so all you need to do is hit your return key, and we can see the map again.
Okay.
I got another call I gotta be on. So.
Yeah, I know we're getting to the end of the guys will complain about this being a long file. I will send you the WMV of this, by the way. It's very rare, as you know, for campus power engineers to get together and to find space on a conference. So I think you can see on the Lawrence, on the other teleconferences, upwards of 50 odd, I think maybe 75 odd views on them. So I think at least among our colleagues, this is very valuable information. But go ahead, Ken.
Okay, can you see the screen again?
Can I ask a question just on the distribution? Because, so how do you manage this? Because we've kind of managed the one lines, not getting, although they've shown people, we haven't released them, so they're community domain, public domain.
Right, they are not.
How are you managing that on this presentation?
Okay, one more time.
How are you managing the one line?
Yeah, there you go. I'm sorry. Yeah, it's clicking on and off here. The question was the proprietariness of this distribution. This is, to answer it, it's generally under the auspices of IEEE. And you can own this. I haven't, no one's really asked for this before. But
it's under ownership, Mike. It's just of Homeland Security and not releasing too much information to public domain. And the only thing that's sensitive is the one line that's in here necessarily.
The sensitive part's not on the one line.
Yeah, the sensitive part's not. So
not on that one line, but
yeah,
understood.
Yeah. So I don't know how you manage that.
Yeah, well, we can black it out. Again, I'll give you the WMV. Well, let's take a look at this. I won't upload it immediately, but we do have Adobe here. I don't have my regular guy, Mike Toner, but I can certainly get that taken care of. But it is a concern, and I think that's one of the reasons why we're always a little bit circumspect about this.
Yeah. Well, I would rather the one lines not get, with the package that gets permanently placed, does not get released.
Yeah. Okay. All right. So we'll work on that a little bit and get it blacked out. There was some editing that has to be done when we got dropped by Citrix. Anything else, Lauren? You always have such good questions. Anything else to ask, Lauren?
I think you ran me dry for today, but I really appreciate the presentation. It's always great to see another campus distribution system and get a different perspective about the history, the operation, the one line. So I really appreciate it.
All right.
And of course, it gives me a chance to verify our agenda. As you know, what I've been doing on the NEC for a number of years, we've made it clear that aluminum is the perfectly usable material on campus power systems, and some of them we're using them at the University of Michigan. This is principally a discussion about the campus, the overall campus power system. But in general, the ability to build standby feeders at 2/3 less costs very often can support your reliability. And then also one of the other agenda items for us is the resistance grounding. Once again, we're putting that out there. You might have learned from the UCal Berkeley presentation that resistance grounding of campus power systems is mandatory, and it has to do with seismic considerations. They want to be able to contain the energy that's released. So as you probably know also from your campus data center, which is a really neat load, by the way, good for you, nice steady load, I imagine, that you have very sophisticated grounding regimes there for reliability. We believe that not only will the migration from solidly grounded campus power systems to at least some parts of them being resistance grounded, will radically reduce flash energy and makes maintenance much safer. And obviously you would get an early warning for a cable failure. So that's another agenda item that we're doing. The solar power project is another really cool one that you guys have, and I hope that maybe you can find some time to tell us about it, because all of the college and university presidents are being assessed on their ability to bring in renewable energy and to contribute to the national power security agenda. I'm sure that your college president's raise will trickle down to you guys. That was a joke. Okay.
We're laughing. Only if it works well.
Yeah, right. Okay. Well, look, guys, thanks very much. We'll take our time in making sure this gets produced to your satisfaction. And as I said, we'll try to get others to contribute as well. And I can't thank you enough for the time. And also for Kane's expertise. We will continue our campaign to advocate for safer, simpler, lower cost, and longer lasting campus power systems through some of the state of Michigan agencies. So thanks very much, guys. I'll close the call. Any other final thoughts? Ken, Bob, the other, Mr. Johnson, anybody? Any other final thoughts?
I think we're set here.
Yeah, we're good. This was a good presentation.
Great.
Appreciate the time.
Great. Thanks very much, guys. You'll see emails with files on them very shortly, okay? Take care.
All right.
Bye-bye.
Okay, thanks. Yeah, see you, Lauren. See you, Mike.
Bye.